Yes.
Okay, let me make this single view. So solving the Schrodinger equation for the ground state energy of various atoms through the Hardref method using Python. And it seems like getting my computer to screen share is more complicated than the actual quantum physics itself. So let's begin. So a bit of a background on quantum physics. Quantum mechanics is considered one of the greatest theories to ever exist in modern physics. It was mainly pioneered in the early 1900s, so it's relatively recent. Einstein contributed a lot to it. Schrodinger, Heisenberg, some of the big names in quantum physics, Bohr too. No experiment to date has been successful in disproving the observed quantum properties for microscopic systems, most notably atoms. And in the past century, experimental evidence has shown that particles can behave both as a wave and a particle. And this is one of the main concepts or ideas of quantum mechanics. It's that the dual wave particle behavior of any particle. So it doesn't only apply to light. Many of you may know about the photoelectric effect, which Einstein won the Nobel Peace Prize for. The Davison-Germer effect also showed that electrons behave as a particle and a wave too. So for this project, we'll mainly be analyzing the wave behavior since we're finding its wave function. So let's begin. So what is the Schrodinger's equation? Schrodinger's equation is a fundamental differential equation in quantum physics. And solving it gives psi, the wave function of the electron. The energy of the electron, along with the probability that the electron is at a certain location, can be described using phi. Now, it's important to note that we can't find the electron's exact position. That's part of the Heisenberg uncertainty principle. We'll never know where the electron is at a certain point. We can only know its probability. For example, I can say there's a 50% probability the electron is between x equals 1 and x equals 3. Let's say it's on a straight line. But I cannot say the electron is at x equals 2. We can never exactly determine that. So for this purpose, we're going to use the time-independent Schrodinger equation, and we're going to assume the atom is stationary. So it's not moving at all. And this is the Schrodinger's equation. It looks simple at first because it's obviously been simplified. The Hamiltonian operator is where most of the differentials are, and that's the energy operator. It basically describes the combined potential and kinetic energy of the system, which yields the overall energy. E is the energy eigenvalue, and psi, the symbol right here looks like a W, is the wave function of the electron. So the Schrodinger equation does have some limitations. Yes, it sounds nice that basically if you find the wave function, it tells you everything you want to know about the atom or the electron. But one, like I mentioned before, it doesn't tell us where the electron is, only the probability it's at a certain point. And also the Hamiltonian operator is different for each atom. For hydrogen, it's really simple, but for many electron atoms like lithium, it gets extremely complicated. And when you go on, it's so big that some scientists don't even bother to find it. We cannot find the wave function of an electron for many electron atoms. And by many electron atoms, I mean anything with more than one electron. So from your chemistry classes, many of you may know that hydrogen only has one electron. And that's the only atom we can solve Schrodinger's equation exactly for. We cannot solve it exactly for anything else. We don't know the wave function for any electron in any atom with more than one electron. But there is some good news. Yes, we may not be able to solve the Schrodinger equation to find the general wave function for atoms other than hydrogen, but we can still use methods to approximate specific values. For example, we can solve it for certain parameters and we can find the ground state energy. Again, these are all approximations because they can never be solved in exact form. And these are all irrational numbers anyway. So yeah. So what is the Hardref method? Now, like I was saying in the previous slide, there are methods we can use to find certain values for these many electron atoms. And the Hardref method is only one out of many for approximating a solution to Schrodinger's equation. Recently, more methods have been pioneered, but the Hardref method was the original method. Most of the papers you see nowadays where they talk about the ground state energy or their results, they all use the Hardref method. And before it wasn't really implemented in code. Sometimes it was done by hand, sometimes it was done by really old computers, but recently people have been using Python and libraries to solve it. So the first step in the Hardref method is to assume that our wave function for the many electron atom is the product of multiple one electron wave functions. So for example, helium has 2 electrons, right? So let's say X is electron 1 and Y is electron 2, or in this case, R1 is electron 1, R2 is electron 2. Essentially think of it as like it's a multivariable function. So f of 1 comma 2. And the first step is to assume it's the product of one electron wave function. So we're saying f of x and y, or f of x comma y equals f of x times f of y. And this really sounds nice. This would solve our problem right there. But there is one issue, which is the main reason why Schrodinger's equation cannot be solved exactly for many electron atoms. And that's because spin states and repulsion. We have to also consider that there are other electrons as well as the one that we're doing this for. And it also violates the anti-symmetry principle, which requires that spin states of the electrons be taken into account. So in order to incorporate spin states into our equation, we have to take the Slater determinant of the system. This is essentially just a matrix right here. And basically what this does is it incorporates every single spin state. So all the possibilities. For example, electron 1 is a positive spin state and 2 is a minus, and then 2 is a minus and 1 has a plus. There's many combinations. We could get into like maybe basically some number theory, or what's it called? Counting and probability here, but we're not going to. So Hardref method continued. Now that we have the Slater determinant, we need to obviously solve the differential equation, and the variational method is then used. So basically, let's say, again, a 2-electron system like I talked about in the previous slide. Look at electron 1 right here. This is E1 for number 2 on this list right here. Number 1 is set up your system, obviously. And number 2 is to solve electron 1 in the average field of electron 2. So first we're solving for the energy of electron 1, and we're saving that value. So a field value is created for electron I, and we're pretending like none of the other electrons exist. After the wave function is created for this electron, we switch to electron J, or in this case, electron 2, and we use this as the new field. The field originally was pure, there was nothing in it. We were solving everything with respect essentially to Z, which is the nucleus. But now that we've solved for electron 1, we're solving for electron 2 in the field of electron 1. And this process is repeated multiple times, minimizing the ground state energy. So this is actually, like many of you who have experience with machine learning may know, that it takes a while to converge. Essentially, all we're doing is making it more and more accurate. But usually after the first few iterations, it's already reached near peak accuracy. From there on, it's just additional computation. So here are some examples of the code, and that is weird because oh my God, sorry. That should not have been cut off, but I guess it happens. So the Python script we used was originally made to approximate the ground state for lithium, but we were able to expand it in order to approximate the ground state energy for boron, carbon, and nitrogen. Essentially what we did was we altered zeta values from the double zeta basis set. That was the main part of our process, but I will cover this in the future slide. But for now, mainly look at the second code sample. Why is this happening? One second. Let's go back here. Sorry, some strange stuff is happening.
It always does, no problem.
Okay, anyway, so if you look at the second code sample here, the one where we're setting FS1, FS2, FS3, this is essentially our processing of the data. Here's where we basically create the parameters that will go into these matrices. And if you look at the first one, the one that starts with the else statement, this is where we actually do all the calculations. So when I was talking about the Hardref method, I really simplified it. You can just solve for I, J, and repeat it. Like there's also a process to solve for it in each field, and that is where we create matrices. So it's just a series of matrix manipulations, and eventually we solve for our Hardref coefficient, which we then use to obtain our final value. The main portion of this code or the most important part of this code that we fixed here or we implemented was the building of the basis functions, which is right here, where we're basically creating the parameters that go into these matrices. So now I'm going to cover what a basis set is. Probably should have done this earlier, but it is important to note. So basis sets are sets of functions that are combined to create atomic orbitals, essentially the ones the energy is solved for by minimizing the Slater determinant. The most common basis set is the STO3G, but we use a double zeta basis set for a project. And the reason is because we're using two functions to approximate each orbital instead of one. So let's say the STO3G might have slightly less accuracy because it's only using one. Here we're using two. So both of them are minimized when we're solving for final ground state energy. So this was our results for lithium, which is the first one we did. Lithium was actually the easiest because we already had the code for helium, which is where I was getting most of the diagrams from. We had the code for helium, which was already done by, I believe his name was Dr. Adam Luke Baskerville from Oxford. He'd already written a code to do this in Python for helium, but obviously we needed to expand to lithium, and we needed to consider when we're going to carbon and when we were going to nitrogen and even sodium, we had to add orbitals as they came along. But lithium was the simplest. The runtime was only 60 seconds, which is around 1 minute, or a total runtime was 68 seconds. And that's really not much time because usually this process could take up like hours. It could take hours for high level electron atoms or high electron atoms, but for lithium, it was pretty simple. And we got a good result. It was negative 7.41, which I'm honestly, there's no correct answer, but it's commonly accepted that 7.41 is the energy level. And this is in Hartrees. Note that it's not in joules. There is a Hartree to joule conversion. I don't know what it is right now off the top of my head, but for those of you who are interested, you can convert this to joules. These were results for carbon. So I'm just going to skip boron because boron and carbon yielded pretty similar results in terms of runtime, and there wasn't too much of an impressive result here. The code for carbon gave us a final value of negative 37.65 Hartrees, and the average runtime was 181 seconds. Now, this is a significant increase from lithium, but it's kind of expected because we're adding a p orbital when we go into carbon, and this requires additional computation. Again, there's no correct answer, but our value was really close to the commonly accepted ones, which was 37.83 and 37.68, and we got negative 37.65. So yeah. Next was nitrogen. Nitrogen, again, was not too many issues here. The ground state energy was estimated to be around negative 53.83 and runtime 187 seconds. Now, the reason why nitrogen and carbon were similar is because they have lots of structural similarities. So the runtime increase was really small, 3.74%. Kind of like from boron to carbon, it wasn't too impressive. No impressive results here. Now, sodium is where things get kind of interesting because, well, our value is completely off from what's commonly accepted. Also, it's because the runtime was 1,512 seconds, which is crazy considering that the last ones were in the hundreds, and this one is just like 15 times everything else. Now, it is a jump on the periodic table from, what was the last one, nitrogen, but that's not the main reason. The main reason is as you add atomic orbitals, the amount of the data processing you need to do becomes more and more complicated because going back to the previous slide, remember where we're solving for one electron in the field of another? It's really simple when you have 2 electrons, but when you have 11 electrons, essentially you need to use some of your combination. You got to do 11 choose 2. So every possible combination of 2 electrons out of those 11, which is the atomic number for sodium, you have to solve them in the field of each other. And that's not a linear trend. When you go from 7 choose 2, which is the case of nitrogen, to 11 choose 2, it becomes huge. And also because we have a 3s orbital, and honestly, I wasn't expecting, none of us were expecting such a big increase from 2p to 3s, but I guess there was a really big one. And there was also a huge jump in accuracy. We have some charts on the next slide that describe how big the jump was, just to give you guys some perspective. And there are some reasons for it. So we have 3 potential reasons. So there was an 8.51% error, which is pretty big, considering that our last ones were less than 1. The percent error was less than 1. And we came up with 3 reasons for the inaccuracy in sodium. So the first one is a bug in the code that needed to be fixed. So going back to what I said earlier, remember we're processing our data to put into our matrix functions, which would then calculate the energy. Perhaps we need additional matrices. Maybe we forgot something for sodium. We really double and triple checked our code and we didn't find anything wrong. But apparently there are 2 matrices in the Hardref calculation called the J matrix and the K matrix, which are important to add accuracy. And I think you can keep going or add even more to those. So we didn't do that. We neglected to do that, and we ran out of time because summer was ending. So hopefully that is something for future research where we properly use the J and K matrices in order to improve accuracy. And the second one is an issue with input data from the double zeta basis set. Now, the website we used to get our double or zeta values was kind of seedy. It wasn't properly maintained or anything like that. We just went with it because it was accurate for most of the other values, and we really couldn't find any other sources. So that could be an issue. Maybe a more official source would be able to yield better results. And the last one is usage of the double zeta basis set. The people who got the more accurate value used the SDO3G set, which is what I was mentioning earlier, but it really shouldn't be that case because the double zeta basis set is commonly accepted to be even more accurate. Because again, we're using two functions to find the energy of orbital energies as opposed to one. So I don't know, maybe more is less in this case, but science should say that the double zeta basis set is more accurate. So in conclusion, I think I can safely say it's a bug in the code, and maybe the addition of J and K matrices would fix it. So like I said earlier, these are our error analysis and runtime charts. As you can see for, looking at the percent error chart, it's actually quite a bit for nitrogen. It's a pretty big jump, but it's huge for sodium. I mean, it goes from less than 1% to 8%, which is pretty ridiculous. And when you look at the average total runtime, this was actually expected. Now that I think about it, because of the possible combinations of two electrons you can choose. But the percent error, I really have no clue why this happened. And we really hope that this is going to be solved in future research, perhaps by an ASDRP student or someone else reading the paper. And our conclusion. So our current research basically estimates the ground state energy for specific elements under and including sodium. As atomic number increases, so does percent error. And we want to continue tweaking our current code for elements with 4 electron orbitals. And that's essentially sodium. We have a 3s, a 2s, a 2p, and a 1s. And perhaps even expand to something with a d orbital, which is something that's really difficult considering that we're already getting pretty bad accuracy for sodium. I mean, how are things going to work when we go to a d orbital? Another thing that we were considering on doing is, well, actually, this is for the next slide, but while our current Hardref code still requires more modifications, it still has proven to be an efficient program to solve atoms up to a 3rd s orbital. So we've done a pretty good job with accuracy until we reached sodium. And the study on the accuracy of Hardref can really be utilized to analyze the most efficient way to calculate quantum mechanical values. And it's also really good to analyze the runtime. So going into applications in real life, there is an application to drug synthesis and organic chemistry. Knowledge of orbital energies and atomic structure is important when you're synthesizing compounds. And one of the main reasons why we skipped elements, we just used boron, nitrogen, carbon, and sodium and lithium is because we wanted to use elements that are commonly used in drug synthesis and elements that have lots of real life application. We also did this to improve computational methods when solving quantum physics problems because there isn't much research when we checked on how efficient certain computers are, which programs are more efficient, and you don't see too much of comp sci being applied to quantum physics, even though it's really important when doing stuff like the Hardref method. But every day, new mathematical formulas and methods are being formulated in order to solve quantum physics problems. And testing these methods and analyzing their performance on certain tasks is really important because future scientists may perhaps figure out ways to fix this. For example, whoever finds out how to fix our sodium issue would seriously boost the efficiency of the Hardref method and implementing it in code. So our group hopes that in the future, another group will solve the issue we found with sodium and perhaps expand to elements with a d orbital, which would obviously come after fixing the sodium issue. Something that we're especially interested in seeing, which I almost mentioned this in the previous slide, but I was waiting for this, is the implementation of the Diis method. So a short explanation on what that is. Like I said, the Hardref method is basically a bunch of matrix manipulations to solve for a Hardref coefficient, which would then essentially can be used to find our final energy. But the Diis is basically a shortcut. So instead of creating all the matrices, we can, or I wish I could take us back to that slide. Let's go back to that slide. Where is it? Right here. Let's do this one. So like you're seeing here, we're basically creating so many matrices, right? The Diis method is a method of basically skipping. So it basically takes you from one matrix to another using a manipulation, a more clever manipulation, instead of having to go through all of these. And it's a much quicker way of solving for the Hardref coefficients, a much faster way of finding the ground state energy, but obviously it would take a lot of time to implement, considering that there's absolutely no code implementation of DIIS for many electron atoms apart from helium. So that is definitely a very difficult challenge, but it's something that we would be really interested in seeing. Okay. I personally, on behalf of the quantum physics group of Dr. McMahon, would like to thank Dr. McMahon for being an amazing advisor. I'd also like to thank ASDRP for providing me with the opportunity to conduct and present this research. We're working to get this paper published in a youth journal right now. And our main hope with this is that someone will take it away and perhaps solve some of these future research questions. So these are basically our works cited. We have tons of works cited, especially considering that we had to do lots of reviews where we're comparing our values. And thanks for listening. So are there any questions?
I have a question comparing Hardref and DIIS. You said with the Hardref method, you started with code that was made for helium and you implemented the higher level atoms on it. Is that correct?
Yes.
So you would be doing the same thing with DIIS?
Not really, because DIIS, you can't just, DIS, for the other ones, you could use the same matrices because the Hardref method is the same. For DIIS, you have to implement a shortcut. I'm not exactly sure where the shortcut takes place, but it's completely different. You have to rewrite some portions of the code, like completely redo it. So it's
for each new atom.
Not for each new atom. You can, I think.
Once you've implemented DIIS for lithium, can you use similar code with a few tweaks to do boron and carbon and nitrogen?
That would be possible, yes.
Yes, okay.
Any other questions? Oh, Miss Johannikia, do you have a question?
Yes. Can you go to your second slide? Sorry, I'm still ruminating with the history. Yes. So if I'm not wrong, you said Einstein got a Nobel Prize, or first, I think you said Peace Prize, but I think
the Nobel Prize for Science.
For quantum physics?
For discovering the photoelectric effect, yes.
For this one? I mean, sorry, I'm ruminating in history because I thought Einstein got Nobel Prize in relativity theory.
Oh no, that's actually
a continuous one, and then quantum physics is discrete. He never got any. I mean, maybe I'm not, aware of it, but as I know, he got only one Nobel Prize for.
Sahar.
Yes.
Einstein is well known, most well known for his relativity theory, but
Correct.
the great conundrum is he did not get the Nobel Prize for relativity, which he believed in. He got the Nobel Prize in quantum mechanics for the photoelectric effect, which he didn't believe in.
Oh, so it was reverse.
It was reverse, yes.
Interesting. Okay.
Yes.
I found it weird too when I heard about it, but that's actually the way it was. It was actually a pretty big controversy when he didn't win it for general relativity, but he won it for something random, or not random, something important, but different to what he originally researched. But yeah.
Interesting, because I was thinking reverse, because I was like, I was ruminating. I was like, wait a second, am I wrong? So I have a question on slide number 3.
Number 3.
Yeah, so, for just like looking at this equation, so the gamma is fixed. Is it the same gamma on both sides of the equation? So is it like, when you have 2x is equal to 3x, so you're looking at some kind of equation like that? So just enlighten me on this. I'm just like a little naive on this kind of equation. So it feels a little weird to me. Dr. McMahon, can you just
I think it would help if you were to expand both sides.
Yeah.
Because the Hamiltonian winds up being a set of differential equations in each one of the directions. And then the energy equation is not a vector equation. So the left-hand side is a set of vector equations. The right-hand side is a scalar equation that gives the energy value.
Thank you so much. Now makes
so-
sense.
So Archit, maybe the next time you present this, you need to give an example of the Schrodinger's equation for for lithium or helium. There are a couple of places where you can get those and show them in more detail.
Yes, I should probably have added one for hydrogen here, but the Hamiltonian operator is not just a variable. It's an operator. It's a bunch of, like Dr. McMahon said, it's a bunch of differentials, and it varies per atom. So the Hamiltonian operator for hydrogen is different for the Hamiltonian operator for lithium, and so on. I should have probably included an example, but yeah, that's how it works.
Thank you. Just one more thing. So I was like very curious why you said in the future work you are helping the other group to resolve the issue. I think you guys can do it. Why you think an other group to come and help? So I was just like wondering why relying on other group to come and help. I think you're in a good progress. Like why you are not having that hope that you will be getting out of this issue yourself and your teammate.
So actually, I'm planning on working on this issue with another group.
Okay.
I'm resumed in ASDRP, but most of my other group members, I think all of them are no longer continuing with ASDRP this year. So I will be continuing, hopefully solving this issue, but the rest of our group.
Are you saying that you're working solo on this one right now?
Oh, not solo. I hope to do this with the next quantum physics group.
Okay.
So maybe this could be a quantum research.
Let me explain a little of this for Sahar. We have a lot of turnover within our groups from time to time. I'm sure that must occur to you too. There will be a continuing group, but the makeup of the group is going to be quite different in the fall than it was in the summer. So there are going to be some new people in and some old people out. And Archit is going to be the one who is a continuity force that helps to understand where we're coming from and where we're going to. The other point that I will make is researcher, what's the word? Collegiality. The fact that as researchers, we do not hide our methods and results from other researchers so that we can publish first. The idea is to present as much as you can, make other researchers aware so that they can repeat your work and that they can do the same kinds of things.
Thank you so much. Thank you. I have no further question. Thank you.
Malia, do you have a question?
Yeah, I remember like at the beginning, you said you made a couple assumptions. So I just wondering like what the background behind those assumptions was and like how you came to those, like how you accepted those.
So we actually solved those assumptions. Like I said, you cannot make this assumption because it would violate the anti-symmetry principle. So we've solved it by essentially turning it into a matrix here, where we're incorporating the spin states into our equation. So you probably know from chemistry class, electrons have different spin states. We can have different combinations of spin states for electrons. So basically the way you solve it is you do something called take the Slater determinant of the system. And that essentially solves this assumption that we're making, or it fixes it. Does that answer your question?
Yeah, okay, that makes sense. Thanks.
Any other questions?
So Kosh, there were a few in the chat window. I don't know if you saw them, but once you've answered those to your satisfaction, I have one or two questions as well.
Let me see. This is a larger. It doesn't, Akash, answering your question about the larger than negative number, the negative number is the ground state energy, where it doesn't necessarily mean stability. It's just the overall energy of the atom. That's essentially what we're finding in Hartrees. I think it would have made more sense if it was in joules, but the Hartree-Fock method finds the final value in Hartrees and not joules. So hopefully that answers your question. But what is your question? whoever was speaking, I couldn't see. Oh, Mr. Chu.
Yeah, I think, well, I think that was an awesome presentation, a very fantastic treatment of the historical and mathematical grounding for your work. You mentioned that you observe a greater error with greater atomic mass or greater atomic number. Is that correct?
Yes, we did.
Do you have any idea of why that might be the case? Like, what is increasing such that as you increase the number of electrons, your calculated numbers deviate from empirical? This is actually a pretty common issue in computational chemistry and in computational physics.
I would be assuming it's because, well, like I said, the amount of when we're solving one electron in the field of another, the amount of combinations of two electrons, that could be an issue. But I would just say it's more computation required, and the more computation you have to do, the more error you'll accumulate. That would be my original guess.
You said it exactly. It's that you have more electrons, and the more atoms or the more electrons you add, the bigger your computational problem becomes, because you're introducing more and more variables, and those variables have a lot of interdependency. Have you considered using any? So this is called electronic correlation, and and people have developed these things called post-Hartree methods in order to either resolve or attenuate the error that's imposed by correlation energy. Have you thought about using those? These are things like coupled cluster or configuration interactions, so CI, full CI or partial CI. If you haven't heard of them, I might suggest looking them up.
That's interesting. We'll definitely consider, or I'll definitely consider looking at those. Would DIIS also be a good option, like I mentioned?
I'm not familiar enough with DIIS to comment on how it would compare with CI or CCSD. But typically people use coupled cluster to resolve these sorts of issues for lower molecular weight or lower atomic weight elements. It would be interesting to see which of these gives the best correction for correlation energy, if you're able to account for that with the IIS.
Okay.
Yeah, I think what you observe is actually what others have also observed, so it's not out of line with prior observations made by a number of people. So this is why CI and CCSD were originally developed.
So it would be interesting to try and compare CI, CC, and DIIS and see how they all differ in how they can approach greater accuracy.
Yeah. So I'm not familiar on the mathematics, and you might discover more about this as you read in and as you become an expert in this, Akash. But the different ways of treating correlation have to do with different variable groupings. That's one of the factors involved. Right, if you have 10 variables, you can treat these 5 variables as a single super variable that might resolve some of the mathematical complexities, and allows you to simplify correlation energies. So you might be able to find some of this code open source, especially with things like, see, Gaussian is proprietary, but there's a lot of open source packages where you might be able to just yank out the CI code and see what's in there. I thought that was awesome though.
We'll definitely take a look at it. If it's as easy to come across as perhaps, obviously I could expand off of it. If it's there for helium, then like we did here, we could expand it to lithium, and it's mainly a matter of just adding more orbitals and changing some parameters here and there. So I'll definitely take a look and see on GitHub if there's any, like you said, CI or any of the other post-Hartree methods. That would definitely be, with my next group, I would definitely love to build upon this research by doing that. And who knows, maybe that might just fix our sodium issue. So thanks for that advice.
It might, yeah. You can also try, I noticed you use a double zeta. You can try a triple zeta. I mean, people have develop these TZP basis sets too. So just some thought.
Okay.
It's,
Hello,
it's
everyone.
good.
Okay. Hello, everyone. I am Harshini Vakalagada, and I am part of the Benson Marine Biology Group, and our experiment was talked about ocean acidification effects on barnacles. Sorry, the slide is not moving. Oh. Okay, so 4 things that I'm going to go over in this slideshow today are the introduction, the methodology of our experiment, and the data that we collected, and a brief conclusion about, sorry about that, a brief conclusion about our data. So what are barnacles? So barnacles are species that are related to crustaceans, and they are commonly found on tide pools and are found close to shore. And for the purpose of our experiment, we chose to use local barnacle species, and we used both Balanus aquila, which are known as acorn barnacles, and Tetracletus rubescens, which are known as volcano barnacles. And barnacles are marine crustaceans that use feathery cirri to filter feed plankton. And the cirri are located at the top of the barnacles, and they have the way that they function is that they sweep the water, the surrounding water, to see if there are any prey that they could feed on, or if they notice that there's something that is harmful, they immediately retreat and go back inside of their bodies. So yeah, and then also they have hard calcium plates that protect their bodies. So that is one way that they can protect themselves. And some background information. So over the years, ocean acidification has been an immense issue that has affected many forms of marine life, and human activities have contributed to a lot of this, and human activities specifically pump more and more CO2 into the ocean, and this is affecting the ocean's acidity and causing the levels of acidity in the ocean, which is also known as pH levels, to continually fluctuate, and this is destabilizing the pHs of our oceans, which is really harmful. And some of the effects of ocean acidification on animals include increased carbon dioxide. They cause defensive behaviors not to be triggered in the barnacles. So the barnacles on top, they have less ability to protect themselves than what they already had. And the barnacles continually need to exert more energy on basic functions, which can tire them out even more and not allow themselves to prioritize other daily tasks that they need to complete. And for our experiment, we will be looking at how barnacles, their feeding habits, and predator avoidance behaviors are affected by ocean acidification. And for our hypothesis, we hypothesized that increased ocean acidification would increase the barnacles Balanus aquila and Tetracleta rubescens metabolic needs, and therefore increase their feeding amount, but will lower their abilities to detect and defend from predators. So now I will be talking about the methodology. So to obtain an accurate analysis of the barnacles feeding rates, we first set up 3 saltwater tanks of varying pH levels and placed Balanus aquila and Tetracleta rubescens barnacles in each tank, and each saltwater tank had a different pH level that signified the present, past, and future predicted ocean acidification levels. So the control tank represented the ocean acidification level that is in the present. So that tank was at a pH of 8.1, and the slightly more acidic tank had a pH of 7.2, and the lower pH tank had a pH of 7.5, and we made sure to distribute plankton to the barnacles by using 2 0.3 millimeter micropipettes. And in order to get effective data, we observed the barnacles twice a week and counted their seri extensions in 1-minute intervals. And the way that we did this was that the intervals were taken in a 30-minute period. So we would observe the barnacles feeding for 1 minute, and then after 10 minutes, we would do our second 1-minute interval. And then after another 10 minutes, we would do our third 1-minute interval, and then going on like that. And we did that 4 times. And the counts were 1 minute long in 10-minute intervals over a 30-minute period, which helped us quantify the barnacles feeding rate. And another important part of our experiment was predator detection. So to achieve that, we had to research what predators the barnacles had, and we found out that starfish was one of them. And to replicate a starfish's physical traits and like how their surface is a little bit it's similar to like sandpapery surface. We used a sponge, attached it to a glass rod, and we lightly brushed across the surface of the barnacle shell with it. And when we placed the barnacle in a beaker, and we used a sponge attached to a rod and lightly brushed the surface of the barnacle. And when we did this, the barnacle did retreat back into its shell, which suggests that in a more acidic environment, the barnacle does have less abilities to protect itself when predators do come. And now I'm going to talk about data and results. So this graph shows the data for sorry, let me just. So this graph shows the data for the barnacle feeding averages. So as you can see, and this is sorry, okay, so as you can see for the control tank, there is not that much fluctuation in the barnacles feeding habits. So at the bottom of this, it shows the days that after the CO2 was placed, and it shows, I don't know if you guys can see this, but it shows 0 days, 4 days, 8 days, and 12 days. And over that time, for the control tank, there was not much fluctuation in the average seri count. So as you can see, from 0 to 4 minutes, the Suri count does not change much for the control tank, which is orange, which goes from 6.3 to 6.8 Suri extensions per minute. And it decreases a little bit from 6.8 to 6.3 Suri extensions. And then it goes from 6.3 to 5.3. So the data is pretty steady as for the control tank. And for the 7.5 pH tank, there is more fluctuations, as you can see. And so the data goes from 3.5 to 8.8 Suri extensions, and then it decreases from another time interval 4 days to 8 days. It decreases from 8.8 to 2.2 Suri extensions, and then it decreases even more. And for the 7.5 pH tank, it takes a similar route to the 7.8 pH tank, but it's the opposite. And the Suri extensions negatively decrease in the beginning, and then they have a big increase, and then they decrease again. And then the figure 2 and figure 3, they go a little bit more into depth into the days. So this one is this data was taken 8 days after we started feeding them, and after the first 8 days, we did a data collection where we measured the feeding rates in every 10-minute in every 10-minute intervals. So so as you can see, for the control tank, it still fluctuates, but it does have a minimal increase from 10 to 20 minutes, and then it tapers off. And for the 7.8 pH tank, it has a big increase in Suri extensions per minute from 0 to 10 minutes, and from 10 to 20 minutes, it has a decrease and tapers off towards the end. And for the 7.5 pH tank, there is more of a decrease in the feeding activity of barnacles. As you can see, the line travels downwards. And for the third pH tank, for the third figure, which was taken 12 days after we started feeding them, the data is a lot more varied, and this can be due to a multitude of factors, like due to the fact that they were acclimating to a new environment, and it could also be because of their new feeding habits in a new environment. So for the 7.8 pH tank, the average Suri extensions fluctuated a little bit, but eventually ended up to be the same amount that they started with. And for the control tank, as you can see, there's a large decrease in average Suri extensions per minute, and then it tapers off towards the end. And for the 7.5 pH tank, there is not much fluctuation in the barnacles' feeding habits, and it just decreases a little from the beginning. And our data at this moment, it is not entirely conclusive, because we still have to do a lot more data collection because our experiment is still ongoing. And for our conclusion, as I said, there is more data is needed to make sure that the data is significant. And just to go over the figures, in figure 1, the feeding rates in more acidic environments could possibly increase initially, then drop as they spend more days in the higher pH levels. And this can be because of the fact that barnacles in the tanks with lower pH require more energy, so they need more quantities of food immediately after acidification. And in figure 2, they had a steady feeding rate with few fluctuations. And in figure 3, the feeding rates highly decreased, as you could see, and showed a downward trend. And going back to the data for the predator avoidance behaviors, it indicates that increased acidity makes barnacles more vulnerable to predators. And in addition to testing the sponge and the glass rod as starfish, we also tried to research if there were any chemicals that the barnacles were sensitive to. And we did find out that trypsin was one of them. And we did try to use it in a beaker with the barnacles, but there was not much effect. And I also found out that capsaicin was one chemical that had some predatory influence to the barnacles. And capsaicin is used in a compound that usually removes them off of ships. So that is one possibility that we are going to consider. And acknowledgements. Thank you to our awesome research advisor, Mr. Andrew Benson, for guiding us and helping us throughout this project. And we would also like to thank the ASDRP program for providing us with the resources we need to become better researchers and perform our experiment. And also, one more note about the data. We hope to collect more data and as the semester goes on and find a more conclusive interpretation of the feeding trends of the barnacles. And this is just my references. Thank you for listening. Any questions? Oh, I see some in the chat. Mr. Downing, you can go first.
Oh, no, I didn't have a question. I was just clapping resoundingly for your presentation.
Oh, thank you.
You are welcome.
I think Archit has an interesting question.
Yeah. Archit, you can ask your question.
I didn't raise my hand.
Oh, sorry about that. Okay. Akash, is it also possible to measure the hardness of the shell to see how it changes with the acidity of the water? I believe that is possible, and I was thinking about doing spectroscopy experiment with the barnacles and using a microscope to sort of like dissect the barnacles, and hopefully that can give me more of an insight into how the shell, how the hardness of the shell changes with the acidity of the water. Ojasvi, do you have any theories or hypotheses as to why predator avoidance behavior in barnacles decreased with increased activity based on your research? I will have to think about that for a moment. Let me go to any other questions. Okay, so I think that we don't have, our data is not conclusive yet, so I don't want to say for sure that higher acidity has negative effects on barnacles. So it might just be because of the conditions of that day that the barnacles reacted negatively to the predatory influences we put in the into the beaker. So I hope that answers your question, but we need to do a lot more data collection in order to confirm that increased acidity would have negative effects on barnacles combined with the predatory influences. Yeah, I can talk about my conclusion. So, okay, so there was also one thing that I wanted to mention for the conclusion. So since the p-values basically they talk about the probability of the accuracy of the data, and so since the p-values for the barnacles were between 0.4 and 0.1, the data was not significant enough to show a change in the volcano barnacle feeding habits, so their data was not included. And as I showed in the presentation, I only showed the data for the acorn barnacles. And for the acorn barnacles, since the data had p-values of 0.002 to 0.09, we can accept that the feeding rates are not only significant, but are also statistically different from one another. And the data sets with the p-value of less than 0.05 are definitely significant, but the p-value of 0.09 is still under the threshold of 0.1, meaning it still has some value and can be considered in our preliminary results. Do you have any specific questions about the graphs, Manav? Okay. Mr. Ahmadi, what type of microscope would you use? I believe I think it's called a dissection microscope, but I am not exactly sure of that. I would need to double check in order to confirm the right type of microscope, but I do believe that I would need one that has a larger scale of magnification than typical microscopes. And in terms of finding more acidic environments, I believe that it's mostly man-made, so it would need to be created in a lab setting. But different oceans do have varying pH levels, so different acidity levels. So there can be a little bit of research done on that, and yeah, but mostly it can be made in a lab setting for like the most accurate results. I hope that answered your question.
I can
Yes, Harshini.
Yeah.
Hi, Harshini. This is Mr. Mahdi. Sorry, I couldn't plug in my microphone and get it working. But thank you. You answered that question. This is a really interesting and great presentation.
Thank you. Did you shake or stir the beaker regularly? Are you referring to the predator avoidance? If you're referring to predator avoidance, we kind of like we like use the rod to kind of like drop the sponge carefully into the water in the beaker. So we didn't shake or stir it because we didn't want to harm the barnacles, but we just wanted to see how it would affect their behaviors. I hope that answers your question. So someone asked, why did you choose to study barnacles specifically? When I got the research question in the beginning of the semester, I was really interested in studying ocean acidification, and I wasn't too familiar with barnacles, but barnacles were a part of the experimental question, so that's why I was interested in learning about ocean acidification, and I got exposed to learning about barnacles throughout this too.
I can answer that a little bit more too. I guess barnacles, so well, this will kind of go back to a previous question too. Barnacles, in terms of ocean acidification, have been studied a good amount in terms of their calcium carbonate shells and what the acidification of oceans does to their shells specifically, and mollusks and crustaceans in general. It typically degrades the calcium carbonate and makes their shells weaker. The barnacles specifically we chose because we wanted to look at crustacean that we wanted to like look at their feeding habits and stuff. And barnacles were the easiest one to do that through. That was at least originally why we chose barnacles. And then as Arshini said, we kind of got more into it. But because you can see barnacles suri extend and all of that, it's an easy way to quantify it. If that makes sense. Great job, by the way, Harshini.
Thank you. Does anyone have any more questions or anything I could clarify or, yeah.